Hello, complex students. Today we're going to be talking about exponential functions and logarithmic functions. I think you'll see that both of these kinds of functions have the familiar properties that you know from previous classes for the real valued versions of them. But there are also some major differences. In particular, the way that we have to define logarithmic functions, they turn out to be multiple valued functions, and so we have to exercise some care before we can start talking about differentiability and continuity and these sort of things. So let's get to it. So first let's define what we mean by an exponential function. So the exponential function is going to be defined as e to the z is just going to be e to the x times e to the I times y, where z is equal to x plus iy. We sometimes use that exp notation. I don't use it very often, but sometimes it's convenient. We've actually played around with this function before in a previous example. And one thing that's clear about this function is that it's defined for all z, any z in the world, because e to the x there, that's just a real numbered thing, and we know that e to the x is defined for any x. And we've previously defined e to the iy to be cosine of y plus I times sine of y, and that's defined for any y. So e to the z is defined on the entire complex plane. And one thing to notice about the form of it, the form of the exponential function, right here underlined in red, it's already of the form r times e to the I theta. So it's already in so-called exponential form. We can see what the radius of the exponential is, and we can see what the angle is. So the modulus, or the radius, of the e to the z is just e to the x. And the argument of e to the z, the angle of it, is y, plus multiples of 2 pi. And there's one little sort of convention that we need to address because it comes up a little bit later when we're talking about logarithms. But if z, our complex number, is really just 1 over n, a real number, the real number 1 over n, then when we see e to the 1 over n, we're not going to interpret that as the set of all nth roots of e. For this special number e, we're just going to interpret that to be the one real nth root, just regular old nth root of e, and not the set of all nth roots of e. So this is an exception to our standard convention that whenever you see any number raised to the 1 over n, you interpret that to be the set of all nth roots. But it just keeps the waters from getting muddied a little later if we do that, so we'll just go with that. And exponential functions have all of these sort of standard properties that you hope an exponential has. For example, the first one here, e to the z1 times e to the z2, would just be e to the z1 plus z2, turns out, just like you hope it would be. And similarly, e to the z1 over e to the z2 would be e to the z1 minus z2. We actually already calculated this in a previous example, but the derivative of e to the z is e to the z. And because the radius, the magnitude of e to the z is just e to the x, and e to the x is always positive, e to the z can never equal 0. Okay, so those first 4 things we talked about are just like it is in the real numbered case. You could replace z with x and you have all those same properties for the real valued version. But something new, or a few things that are new, is that for one, e to the z is a periodic function. So periodic just means that you can add a certain amount to an input and you get back to where you started. So for example, if you do e to the z plus, then you just add 2 pi I, then you get e to the z times e to the 2 pi I, according to that first property up there. And then e to the 2 pi I is equal to 1, so this is just e to the z. So the period of the exponential function is 2 pi I. That's interesting. It has a period, but the period itself is a complex number. Not just a real numbered period, but a complex period. It can work out that e to the z can be negative. That's different than when you're talking about real numbers. For real numbers, e to the x is always greater than 0. You can think about the graph of the exponential. It kind of approaches the x-axis asymptotically, but it never quite makes it there. or never crosses it. But for e to the z, it can be negative. I mean, a quick example of that is e to the pi, or e to the I pi. E to the I pi is -1. So that's different than the old exponential. Just something I wanted to note here. This is something we'll essentially prove when we start talking about logarithms. But any non-zero complex number is the output of the exponential function. So the exponential function is onto the complex numbers minus the origin. Just as a quick example of that, you could take as example, let's let w equal, say, 1 plus square root of 3 times I, and let's find z such that e to the z equals w. Well, let's see. E to the z we know is e to the x times e to the iy, and we want that to be equal to w, right? And so the idea is we want to figure out what x and y have to be here. But w, I think if you think about it, you can see that the radius of it, that's just the imaginary part squared plus the real part squared, then take the square root. The radius is 2, and I think you can convince yourselves also that the angle is pi over 3. So w here is equal to 2e to the I pi over 3. And then, so we can put that in place of w there. And so the idea is that, you can equate the radii here, and then also the angles have to be at least, the angles have to be, the difference between them has to be a multiple of 2 pi. So here we could say that e to the x has to be 2, and y has to equal pi over 3 plus 2 pi n for some integer n. And then that first equation, if e to the x is 2, then I can see x has to be natural log of 2. So I can see what my x and my y have to be here, so that tells me what my z is. So anyway, so we know our z, of course, is x plus iy. So we get natural log of 2 plus I times pi over 3 plus 2 pi n. I mean, any of these, any such z, if you plug it into e to the z, you're going to get back that number w as an output. Okay, to verify the sum of exponents property for the exponential function, let's set z1 equal to x1 plus iy1 and z2 equal to x2 plus iy2. And then we'll just straight up compute the left-hand side and then reduce it to the right-hand side of the expression above. So e to the z1, e to the z2 would be, according to the definition of the exponential function, e to the x1, e to the iy1 times e to the x2, e to the iy2. And then we can mix around the terms, use some commutativity here, and get e to the x1, e to the x2, e to the iy1, e to the iy2, which we could then write as, using properties that we already know, we know the first part here is, those are just real numbers, so we can use the property of real numbers that says that that's e to the x1 plus x2. And then the second thing, this is something we worked out about Euler's formula earlier, that this can be written as e to the I times y1 plus y2. So that's just a known property that we verified earlier. And now you can see that this is exactly e to the x1 plus x2 plus I to the y1 plus y2, which then you can separate out into x1 plus iy1 plus x2 plus iy2, which of course is e to the z1 plus z2. This step up here may look like we're sort of begging the question of adding the exponents together. I mean, the question that we're trying to answer is that we can add the exponents together, right? It looks like we're just assuming the result that we're trying to prove, but actually this is just using the definition of exponential here. I mean, e to the z is defined to be e to the x, e to the iy, right? But z there is x plus iy. I'm not really cheating here. I'm just using, because the first part is a real number and then the second part's I times an imaginary number. I can get away with that. All right. So anyway, there we've proved that one. And once you have the property for the sum of the exponents, you get the property for the difference of the exponents pretty readily, because you could just do something like e to the z1. Well, you could put in a well-chosen 0 and write this as e to the z1 minus z2 plus z2. And now you could use the property that we already proved for the sum of the exponents and write this as e to the z1 minus z2 times e to the z2. And then we know that e to the z2 is not equal to 0. That was one of the properties of exponentials. So we can divide both sides by z2, or e to the z2. And you end up with e to the z1 minus z2 equals e to the z1 divided by e to the z2, as advertised. So we kind of get that one for free. All right, so the exponential function is pretty straightforward to define and work with. Now we come to the logarithm. The logarithm is a bit more complicated. So the idea of a logarithm is you sort of define it to be the inverse of an exponential function. And so what that comes down to is you want to solve this equation, e to the w equals z, and you want to solve that for w. So if someone gives you a z, you want to figure out what the exponent has to be so that e to that exponent would equal z. So this is essentially working the exponential function backwards, right? Usually with the exponential function, you provide the exponent as the input, and then you get some answer by taking e to that exponent. But the reverse process would be to say what the result is and then have to come up with what the exponent is that gives that result. So let's just do that. Let's just figure out, like, how do we solve that equation, e to the w equals z for w? So to start with, we got to put our two numbers that are involved here into some sort of complex number form. It'll be convenient to take the number z. So z is sort of the given, and we'll write it in its exponential form. So r times e to the I times that capital theta. Capital theta is just like the principal argument of z, okay? W, we're just going to write it in sort of a standard complex number form, u plus I times v. So then if we say e to the w equals z, that's the same as saying e to the u plus I times v is equal to z, which is r e to the I times capital gamma, or capital theta. And then according to the definition of exponential function, the left-hand side of this last equation is e to the u times e to the iv. That equals r e to the I times that capital theta. And just like with the example we did a little bit ago, this is only going to be true if e to the u is equal to r. And remember, we're trying to solve for w, which is the same as solving for u and v. And we know that e to the iv is e to the I times this capital theta. So then that first equation tells us that u has to be the natural log of r, just the regular old real number natural log. And we know that if e to the iv equals e to the I theta, the difference between those two angles, v and theta, has to just be some multiple of 2 pi. So we know that v has to be this theta plus 2 pi n, where n is just an integer. So we got our w there. So w is the logarithm that we're looking for. It's the exponent that produces a certain z. That's how we think of logarithms. Like, back in the old days, if I said, hey, what's log base 3 of 27, what I'm really asking you is 3 to what exponent equals 27, right? And so the answer would be 3. So we just solved for the logarithm here. So that's how we're going to define the logarithm, log z. So log z is going to be natural log of r plus I times whatever our v was. So our v was this capital theta plus 2 pi n. And here we're remembering that our z is equal to r e to the I times that theta, where theta was in the right interval, negative pi, positive pi, possibly included. And then remember r is just the magnitude of z, so I could write this as natural log absolute z plus I times this expression in the parentheses here is just arg z. So you could just write this as arg z if you want. So here's our logarithm. One thing to notice about this log function is that it's not a regular function, it's a multi-valued function. Sometimes these are called multi-functions for short. But if you put it, it's not like if you put in a single z, you get a single output. You get, a whole set of outputs, right? So we're going to have to deal with that issue that the logarithm doesn't have a unique value associated with it. It's got a whole infinity of values, a whole set of values associated with it. Of course, what our derivation up here shows, the thing that we solved for was the exponent that would result in z, right? And so we immediately get this identity here that e to the log z is equal to z, just because we were solving this equation here, circled in red. That was the equation we solved, right? W was the logarithm, so e to the logarithm equals z. So we kind of instantly got a nice little identity here, which should look kind of familiar. Like we had the corresponding identity for real numbers, right? Like e to the natural log of x is equal to x. It's just the analog of that. In fact, we can think of that familiar identity as a special case of this identity that I've got highlighted in green here. Because if you set z equal to x plus 0 times I, like here, then log z, if your y is equal to 0, log z becomes natural log of x plus I times 0, that's your angle, plus 2 pi n. And then from there you get e to the log z is e to the natural log of x plus I times 2 pi n. So that's e to the natural log of x times e to the I times 2 pi I, or 2 pi n, e to the I times 2 pi n. But that's equal to 1. So you get e to the natural log of x times 1. So that is the left-hand side of this identity up here. And then z equals x is the left-hand side. So this becomes e to the natural log of x equals x, which is our familiar identity for real numbers. So it falls out of our more powerful identity in green there. So on the previous page, we had e to the log z is equal to z. And the reason this one worked out so nicely is because the exponential function, it's not a multifunction. The log is, but it turns out that even like the exponent here was really a whole bunch of different exponents, but the way that they were different didn't really affect the outcome. You always get z as the output. But when we do it the other way, log of e to the z, we want the log and the exponential to be inverses of one another, so we're kind of hoping that this will be equal to z. But it turns out, no, it doesn't quite work out that nicely. The way that it does work out is as follows. Log of e to the z ends up being z, but plus something extra. That extra bit being 2 pi n times I. So let's verify that. So the logarithm up here somewhere, let me write, remember our formula for logarithm is log of just whatever you put in there, z, is natural log of the modulus of z plus I times the arg of z. And remember arg, little a arg, is a whole set of angles. It's not just a single number. Applying that to what we have at the bottom here, log of e to the z would be natural log of absolute e to the z plus I times arg of e to the z. If we're thinking of our e to the z here as e to the x times e to the iy, then we're looking at the natural log of the modulus of e to the z would be e to the x. And the arg of e to the z is just y plus 2 pi n, where n is an integer here. And then natural log of e to the x, we're just talking about real numbered stuff here, that's equal to x, as we verified a little bit ago anyway, I think, plus, and we get iy plus 2 pi n times I, which the x plus the iy is just z, and then the 2 pi n I, well, that's just what we said we were supposed to have. So that verifies what we were claiming earlier. So that's the same as that identity there. We kind of get that identity, that sort of inverse identity that we were hoping for, but there's a little something extra because of the fact that the logarithm is a multifunction. Part of what we're going to start sort of grappling with is how do we deal with the multifunction? And of course, what we tend to do is we just restrict it in such a way that it only produces one value. And one way we do that is to talk about the principal value of the logarithm. So the principal value of log z is just where we choose the angle to be that one special angle corresponding to the argument of z. So the principal value of the logarithm of z is going to be, okay, you still do like you did before, you do the natural log. Well, I guess in terms of what we have here, it'd be the natural log of r. If we're saying z is equal to r e to the I times capital theta, we'd get natural log of r, and then plus theta, and the part where you have 2 pi, well, I guess there's an I here, I times this capital theta plus 2 pi n, we're just going to take the n to be equal to 0 here. And so that gives us just I times that capital theta. Capital theta there is just the principal argument though. And so we could rewrite this in the form natural log r, little r is the modulus of z, and then plus I times the principal argument of z. It's a nice way to look at that. And of course, if z is actually just a real number, then the principal logarithm of z just ends up being natural log of x, right? Because the argument would be 0 for a real number, and z just collapses to x. And so in the formula in yellow just above, you'd have natural log of the modulus of z is just x, or natural log of x. And then the other part's equal to 0. So the point here is that the old natural logarithm is just a special sort of part of our new kind of logarithm that we have here, the principal logarithm. All right, so just let's just do some very concrete computations just to make sure that we understand how to actually calculate a logarithm of something. So let's start with this first one, z equals -1 minus square root of 3i. For me, it's helpful to draw a little picture of this number to think about what quadrant it's in so I can kind of visualize what the angle of it has to be. So -1, and then negative square root of 3 is like -1.7. So, it's about here somewhere. Sort of think of it as a vector. Looks like this. And I can see that its radius is square root of -1 squared plus negative square root of 3 squared. So that works out to be 2. And by looking at this little quadrant triangle here, I can see that tangent of theta equals y over x. So it's negative square root of 3, which I'm going to kind of think of as, negative square root of 3 over -1. That's positive square root of 3, which I can kind of think of as negative square root of 3 over 2 over -1/2. And I know that that happens at the angle 4 pi over 3. So the complex number that I'm starting with, if I put it into its exponential form, it's 2e to the 4 pi I over 3. And it's nice to put the number into complex, or put the complex number into exponential form if you're going to compute the logarithm of it, because it makes it easy to see what the modulus is, and it makes it easy to see what the argument is. If I wanted to do the principal argument of this thing, I could write it as 2e to the -2 pi I over 3 to get the angle in the right interval. So I could say, well, the log of z, okay, according to our formula earlier, it's natural log of the modulus of z plus I times the arg of z. So that would be, I could write it in this form. I could write it natural log of 2 plus I, and then the argument I could write as 4 pi over 3, and then you got a plus 2 pi n, where n, of course, is just any old integer. I could also do the principal logarithm, capital Log of z, and it works almost the same way. You just do I times the principal argument of z, and so that'd be natural log of 2 plus I, but then the principal argument is negative 2 pi over 3. So notice that the capital, the principal logarithm is a single value, because we've restricted the function's, possible angles there to make it not a multifunction anymore. It's just a regular old function. I mean, we could do the logarithm of 1, log 1. Here we don't have to do much thinking. We know that the modulus is equal to 1, and we also know that the argument is just any angle of the form 0 plus 2 pi I. So this will be natural log of the modulus of 1, which is just 1, plus I times the argument, which is 0 plus 2 pi n. So log of 1, okay, natural log of 1 is just 0. So you get 0 plus just then 2 pi n I, or just simplifying, it's 2 pi n I, n being an integer. So log of 1 isn't just a single number, of course. It's a multifunction, but all the values are of that form, 2 pi n I. But if you do principal log of 1, it's natural log of 1 plus I times just the 0. So this comes out to 0. Or z equals negative 1, the regular multivalued logarithm at negative 1. Okay, we know the radius of that is 1, so we get natural log of 1 plus I, and then we could take the argument. It would just be pi plus 2 pi n. Or we could simplify that just by saying it's I times pi times 2n plus 1. So it's sort of like the odd multiples of pi. And then the principal log, the principal value of the logarithm would be natural log of 1 plus just I times the principal argument, which would be pi. So just I times pi is the principal value of the logarithm on negative 1. And, we're going to have some identities coming up about logarithms. And these examples here are to urge some caution about properties of logarithms that you might just start thinking you have just for free. But yeah, logarithms, we have to be very careful with them. So in this first example here, we've got two different things. One thing is true and one thing is not true. So in this thing that I just highlighted green here, in that example, it's basically saying, hey, you can do the common thing that you do with logarithms where you pull down exponents. But if you change the complex number a little bit, all of a sudden it becomes not true. So let's see why this is true real quick. Hopefully you recognize real quick that with 1 plus I here, the radius is going to be square root of 2, and the argument of that number is, so 1 plus I, it's in the first quadrant there at 45 degrees, right? So the arg is pi over 4. In the one highlighted in blue here, this one's in the second quadrant, negative 1 plus I, so it's still got a radius of square root of 2, but its argument is 3 pi over 4. And we'll see that that kind of makes a big difference, what that argument is. Okay, so on this one, the left-hand side works out to be, okay, the log of that would be, okay, if you square it, it's just going to have the effect of squaring the radius and then doubling the argument. So you get natural log of 2 is the radius squared, plus then you get I times the argument of that squared thing is going to be pi over 2, and plus 2 pi n. Well, the n is going to be 0, so you just get times 2 pi. And on this side, you'd get 2, and then times the quantity, the logarithm of 1 plus I, the r is square root of 2, so you'd get natural log square root of 2, plus, and then I times the argument of 1 plus I is pi over 4. But hopefully you can see that these two things actually are equal, because if you multiply that 2 through on the right-hand side, you get natural log of square root of 2 to the 2. You can use that property of the natural log for real numbers, and then I times pi over 2. And so, yeah, now you see that it's really the same. But on the other side, the log of negative 1 plus I quantity squared. Okay, it's the same thing happens. Your radius gets squared and your angle gets doubled. So on the left-hand side over here, you would get natural log of 2 plus I. When you double that angle 3 pi over 4, it's going to become 3 pi over 2. But 3 pi over 2 is not a principal argument for that number. The principal argument would be negative pi over 2. So the principal value of the logarithm would be natural log of 2 plus I times negative pi over 2. But on the other side, you'd get 2 times and then log of natural log of square root of 2. But then I times the argument of negative 1 plus I is 3 pi over 4. And yeah, these are not equal. It's because, by doubling that angle, we went over the threshold where you get the principal argument of the number. The principal argument lies between negative pi and positive pi. So when we doubled 3 pi over 4, we sort of went past pi, and sort of the odometer rolled back around to negative pi over 2. So that's sort of a typical thing that happens with these. And the next example, I think I'm going to make it a homework problem, but it's even a little bit more extreme. I just want to point out what sort of might be part of the difficulty with it. The first thing, the equation that's true on the left is really hard to read as an equation. There's a little bit of ambiguity here because when you see I to the 1/2, that's actually 2 values. Because remember, when we say I to the 1/2, we're talking about all of the square roots of I. So there's actually 2 of them. One of them's just the point on the unit circle at pi over 4, and the other one's at the angle pi over 4, 5 pi over 4. So you actually have to sort of make an argument about the set on the left equals the set on the right. See, those are really just both sets of numbers, right? It's a little less ambiguous on the right-hand side, and that one's easier to argue that those things aren't equal. But yeah, I'll let you do this one as a homework problem. But you see that it's the same thing. It's telling us that we can't necessarily pull down the exponent like we hope we can with logarithms. So now we got to start getting into this ambiguity bit. And so we start talking about branches of logarithms. Okay, to start off with here, we just got z sort of written in a standard form, and we're assuming z is non-zero here. And we've got our logarithm sort of written out in its full glory here, just to remind us. Just to make things a little easier to look at, this multiple of I on the right-hand side of this, we're just going to call that theta. Okay, so theta is going to be capital arg z plus 2 pi n. So we're going to write log z as just natural log of r plus I times theta. But just remember, when you see theta here, it's not just a single angle, it's a whole bunch of angles. It's basically the argument, little a argument of z here. Next, we're going to pick a real number, alpha. Could be positive, could be negative, doesn't really matter. And we're going to require our angle theta, our argument of our complex number, or z, we're going to restrict it so that it can't take on so many different values. We're trying to get around the fact that this logarithm has so many different values. So what we're going to do is we're going to restrict our alpha to satisfy the inequality. Theta is going to be greater than alpha but less than alpha plus 2 pi. When we do this restriction, log z equals natural log of r plus I times theta. So now we've got theta trapped between alpha and alpha plus 2 pi. Then we know that the logarithm only gives a single value, so log z is a single valued function at this point. So we put a restriction on the angle to eliminate the ambiguity that the function has. By restricting that angle to be between alpha and alpha plus 2 pi, what we've essentially done is we've said what our domain is, right, for our function. If you look at that picture on the right, there's that dashed ray coming out of the origin. And it's dashed because what I'm trying to indicate there is we're looking at the entire complex plane, not including the origin and all the points on that ray. So I'm going to define this domain B alpha to be sort of informally, it's C minus the alpha ray in the picture there. But more formally, it would be the set of complex numbers of the form e to the I theta, where r is positive and theta falls between alpha and alpha plus 2 pi. So this set up here, that's B alpha. And now we've got our logarithm restricted. It's defined on almost the entire complex plane, except for the points on that ray, including the origin. And we can just now look at it and go, hey, on this domain, this is a continuous function. Because you can look at the components of it. The component functions of our logarithm now are just the u, the real component is natural log of r, and the v component is theta. And we can do, Cauchy-Riemann on it. Well, first of all, we can just look at u and v and say, hey, those are continuous functions because what we know about real valued functions, right? Certainly u equals natural log of r. If we think of r as the parameter, that's continuous on its and for positive r's. And if theta ranges from alpha to alpha plus 2 pi, v is continuous on that domain. We got good and continuous component functions. And so then we can also compute the partials, like u sub r would be 1 over r. Just, the derivative of natural log of r with respect to r is 1 over r, just like it always has been. The derivative of u with respect to theta, well, there's no theta there, so you just get 0. The derivative of v with respect to r similarly is 0. And the derivative of v with respect to theta would be 1. And we can see that the Cauchy-Riemann equations hold. Remember, the polar form of those, we need r times u sub r. Okay, r times u sub r is equal to, that'd be r times 1 over r, which is equal to 1. But that's exactly equal to v theta. And if we look at u theta, that's equal to 0. But that's certainly equal to negative r times 0, right? Or in other words, negative r times vr. So point is, here's the Cauchy-Riemann satisfied. r equals v theta, and u theta equals negative r vr. And all those technical little bits about the partials are continuous and they're defined on the neighborhood of the point. That's all kind of trivially satisfied for this domain that we're talking about, this B alpha. So that tells us that, the sufficient conditions for differentiability are satisfied. So now we know our logarithm function is differentiable on that set B alpha, and we can calculate the derivative. We had a formula in that sufficient conditions theorem that said, in the polar form, that the derivative would be e to the negative I theta times u sub r plus I v sub r. Well, we can write down what that is real quick. That'd be e to the negative I theta times ur is 1 over r, and then vr is 0, so you just get 1 over r there. Well, that's the same thing as 1 over r e to the I theta, which is equal to 1 over z. And this was true for any branch of the logarithm. So that's what we call this, this restriction of our logarithm. It's called a branch. So in particular, if I took the angle alpha to be equal to 0, that's how you get the principal logarithm, capital LOG. So its derivative is 1 over z also. So good news. At least the derivatives of logarithms act just like they did back in, single variable calculus class. The derivative of log is 1 over z. And it doesn't really matter how you restrict your theta as long as you restrict it to sort of a full 360-degree circle there based on some angle alpha. So I just want to point out here that for the principal logarithm here, the alpha was equal to 0. Well, that's not quite right. Alpha would be, I guess your cut would be negative pi. Because it goes from negative pi, and then you add 2 pi to that, you get positive pi. Right, okay. So a little bit of terminology. I started using it already on accident, but that ray, that alpha ray that comes out of the origin, is called a branch cut. So the branch cut is just that line. And then when you take the logarithm, log z equals natural log of r plus I times theta, where you make theta range, from alpha to alpha plus 2 pi, we call that a branch of the logarithm. And then log, capital log, log, the principal log, is often called the principal branch of the logarithm. And of course, like I said previously, its branch cut is alpha equals negative pi. And I want to make a little statement. If you look at points that are on the branch cut, like take a z that's right there on the branch cut, like all around that dotted line, the function's well defined. So if you just sort of an open disk around it, you have nearby points on either side of that where the function is differentiable. Or in other words, like if I took a point over here really close to z, I could find a disk around it, and on that entire disk, the function would be differentiable, the derivative being 1 over z. Even though the function itself is not defined at that z, it's not differentiable at that point, it's differentiable all around it, sort of. So that's what we call a singular point, you may remember. So points on the branch cut are singular points of the branch cut. Points on the branch cut are singular points of the corresponding branch of the logarithm. Okay, so let's check out a few things here. So here I've got a branch of the logarithm, and you can see the branch cut is at pi over 4. And so we consider the angle starting at pi over 4 going up to 9 pi over 4. So with that definition, we could look at log of I squared. Okay, so that's the same as log of negative 1. And log of negative 1, the angle of negative 1 is pi, right? That's the angle that falls within the yellow region of angles, right? So this would be, okay, take natural log of the modulus of negative 1, which is just 1, plus I times the angle, which would be pi. So this comes out to I pi. And then if you do 2 times log of I, okay, for I, the angle is pi over 2. That's the right angle in this yellow region, right? So I'd get 2 times, and then the modulus is again 1, plus I times its angle, which is pi over 2. Natural log of 1 is 0, so you end up with, again, you get I pi. So the point here is that, hey, it looks like you have the exponent pulling down property going on this branch. But if I was working on a different branch, it might not, the same sort of equation may not be true. So the sort of identities that you have can vary by what branch you're on. So now I'm on this different branch. Let me shade that branch in green. So now we're only going to consider angles between 3 pi over 4 and then add 2 pi to that, and you get 11 pi over 4. In that case, log of I squared, which is log of negative 1. Okay. The right angle here would be pi. Right. So you get I pi. But when you do 2 times the log of I, you get 2. And then for log of I, the angle, we want it to be pi over 2, but pi over 2 is not in the green interval. So we got to go kind of around one more time and come out to 5 pi over 2. And then, of course, that comes out to 5i pi. And we can see these things are definitely not equal now. So the point here is that, saying that, something like log I squared equals 2 log I is not something you can make as an absolute statement. It's depending on what branch you're on, right? You got to know what branch you're dealing with. Okay, let's talk about some identities that are sort of universal. So the four that I have listed here that I'll give you the right-hand side for are sort of absolute identities, but you have to understand that these are, we're back to, I haven't specified any branches on these. So we're talking really about sets of numbers. It's like the first one says the log of z1 times z2. We can write that actually as log of z1 plus log of z2. You just got to remember that this isn't talking about a single number. Log of z1 is a whole collection of numbers, and log of z2 is a whole collection of numbers. And it's basically just saying the collection of numbers on the left is equal to the collection of numbers on the right. So it's like a statement about sets, really. Similarly, we do have the familiar log of z1 over z2 is equal to log of z1 minus log of z2, understood as, these are multifunctions, and so we got a collection of numbers on the right, or a difference of two sets of numbers, equals the set of numbers on the right. This one's kind of a nice one. Sometimes this is called a change of base formula. But z to the n can actually be written as e to the n times log z. And z to the 1 over n, now remember z to the 1 over n isn't just the nth root of z, it's the collection of, it's the set of all nth roots of z, right? So we're talking about a set of numbers here. And that one is, of course, going to be e to the 1 over n times log z. The interesting thing is, like, we already know z to the n, it has definition in the third one, but it seems to appear that, z to the n could have multiple values because log z has multiple values. Those multiple values sort of all cancel out. They'll end up being the same thing. But on the other one, z to the 1 over n, we know that there should be at least n different values there, right? And that's what we'll see when we go to verifying this. All right, so let's just start with the first one. Let's verify the sum property, or the product property, whichever one you want to call it. The log of z1 times z2 equals log of z1 plus log of z2. Let's verify that. Well, you just follow the definition. So log of z1, z2. According to the definition, this is natural log of the modulus of z1 times z2 plus I times the argument of z1, z2. And then I know that modulus I can break up as a product. So this is natural log of the modulus of z1 times the modulus of z2. And way back when we were talking about arguments, we proved actually that the argument of z1, z2 is equal to the argument of z1 plus z2. It's also a property of just regular old logarithms that the logarithm of x times y is equal to logarithm of natural log of x plus natural log of y. So this first term here I can break up as natural log of modulus z1 plus natural log modulus of z2. So that's just a property of real numbered natural logs. And then I times, we proved argument of z1, z2 is argument z1 plus argument z2. And then you can just put the appropriate terms together here. So we can write this as natural log modulus z1 plus I times arg z1 plus natural log modulus z2 plus I times arg z2, which is by definition natural log of z1 plus natural log of z2. If we wanted to verify the next property, it's actually a little easier to just show that both sides reduce to the same value. So if we started with z equals r e to the I theta, so I could look at z to the n. Well, z to the n is just r to the n, e to the I n theta. But we could also look at e to the n log z just according to that definition. Well, this would be the same as e to the n, and then log z is, by definition of log, ln mod z plus I arg z, like that. And then we could break this up into e to the n natural log mod z times e to the I times n times arg z. But that's the same as e to the natural log mod z to the n there. And then the second term there, e to the I n arg z, is just the same as theta, right? I mean, theta is just the angle. I mean, you can choose any theta that you want that's in the arg. So, and then e to the natural log of modulus z is modulus z. But modulus z is r, so this is just r to the n times e to the I n theta. And then you see that these terms here and here equal to one another. So that verifies that identity. Verifying the one for the nth roots of z to the, verifying the one for the nth roots of z is a little bit trickier, but not that much. We know what z to the 1 over n is. Z to the 1 over n, we had a formula for that. That's like these numbers of the form. You go r to the, you take the nth root of r, and then you do e to the, whatever its angle is, theta, divided by n plus, there's an I there too, plus 2 pi k over n, like that. So this is your nth roots. Of course, we understand that k here goes from 0 up to n minus 1. Then on the other hand, you can look at this e to the 1 over n log z. Well, let's just see what that comes out to. That's e to the 1 over n log z is natural log modulus of z plus I arg z. So that's the same as e to the 1 over n. I'm just going to write that as natural log of r plus, and then the arg z, we know that that's like whatever the original theta was plus 2 pi k, right? But here k is just any old integer. Okay, so let me break this up a little bit. So now if I can write this as e to the 1 over n times natural log of r times e to the I times theta. I dropped my 1 over n. There's a 1 over n times I times theta plus 2 pi k. And then that first term there, e to the 1 over n times natural log of r, you know, I think you can probably see that that's actually just r to the 1 over n times, and then what we have on the next term is e to the I times theta over n plus 2 pi k over n. And now because of the 2 pi there, we know that, you know, as k cycles through the integers, you get a lot of repeats, right? And so the unique values are going to be when k is equal to 0, 1, 2, all the way up to n minus 1. And then all the other values of k give you repeated values of the argument up there. And so, yeah, so they're the same, right? Look, r to the 1 over n, that's just the nth root of r, right? The regular 1 over nth root for real numbers. So you can see that they're the same. All right. Okay, in this last example, I want to revisit the identity that says log of z1 times z2 equals log of z1 times log of z2. But I want to point out why it's very important to know what branch of the logarithm you're dealing with, or what branch is. So let's just remind ourselves here about a couple of things we computed earlier. Log of 1 works out to be 2 pi n times I, where n is just any integer. And we also saw earlier that log of negative 1, you get pi I times 2n plus 1. So you get the odd multiples of pi I. And then if we want the principal logarithm of z1 times z2, now z1 and z2 are both equal to negative 1 in this example. And I can see pretty quickly that, well, z1 times z2, that's negative 1 times negative 1. So we're looking at log of just 1 here. And log of 1, we know that the modulus is 1 and the principal argument is 0. So you get natural log of 1 plus 0 times I. So this just works out to be 0. Or you could get that just by putting in n equals 0 right here too, right? And similarly, to get log of z1 and z2 individually, those are both equal to negative 1, right? Well, the log of negative 1 there, your argument is pi. And so you just end up with I times pi for those two principal logarithms. Again, you can get that by substituting into this n equals 0 too. You see that that identity doesn't hold for the principal logarithm. You do not have log of z1, z2 being equal to log of z1 plus log of z2 when all of those logarithms there are the principal logarithm, the principal branch. Because the left-hand side of that equation we just computed, works out to 0. And on the right-hand side, you'd get I pi plus I pi, which is 2I pi. Certainly 0 is not equal to 2I pi. So this isn't saying that that identity is just wrong. It's just saying that you can't necessarily use the same branch of the logarithm for each of the three logs that are in the identity. What it turns out to be is that once you pick two of the logarithm, like two of the branches that you want to use in that identity, then the third one is determined by that choice. I think I didn't say it out loud, but I had it written over here when we were talking about this identity that possibly not all of the logs are on the same branch. So the same goes for the difference formula too. So you just have to be careful of that. But yeah, you can pick two of the logs, and that'll determine what the third one has to be in those two identities. For example, let's say I wanted to use the principal log for the z1 times z2 part of that identity, and then I wanted to use the principal log for the log of z1 part. Then the question would be, what log do I have to use for this last term in this identity? Well, we already know the left-hand side of this equation is 0, and we know that the principal log of z1 was pi I. So we know that we need the last term to, if this sum is going to work out, we need negative pi I, right? So you could ask yourself, what branch would give you negative pi I? Well, you just got to pick a branch that contains the angle negative pi there for the argument of -1. And there are a lot of possible choices you could use just to visualize it. So here's the angle negative pi, and I need to get a range of length 2 pi of angles that contains negative pi. So maybe I could start here at, maybe I could take my cut to be, so I'm thinking of it like this. Like this is negative 3 pi over 2. And then as you advance forward 2 pi like this, then you'll end up at positive pi over 2 by the time it comes back around. And negative pi would be there in the middle, right? So I think I'll use the branch with my alpha equal to negative 3 pi over 2. And if I do that, then I will get this answer for log of -1 would be negative pi I on that branch. And then you see the identity works. So anyway, it's sort of a subtle thing. You have to really think about these logarithms. They're a little tricky. Okay, I think I'll stop there. I'll talk to you again soon. Bye.